Alright, so we're looking at section 4.5 on first order linear equations in this little video. First order linear equations. Now, we're going to start off with a definition for you of the type of differential equation that we're considering here. So, we start off with a first order linear differential equation in what we're going to call standard form, meaning the form from which we want to actually work problems. This is given as this form: the derivative of y plus some function of x times y equals another function of x. So the reason this is called a first order equation is simply because we only take the first derivative in this entire differential equation. The reason it's called linear is because this looks like a linear equation. You've got a constant, in terms of y at least, a constant times y to the first power occurring. Now, in this standard form, we can use this technique of what's called an integrating factor to help us. So let's define that. And once we have the definition, we'll see how to use it. The integrating factor for a first order linear differential equation in standard form is the following, and we define it as this function we're going to call mu of x, which is simply the e exponential function raised to the power of the integral of the p of x that is occurring right here. In other words, once you have your standard form for your first order linear differential equation, read off the coefficient of the y. Take that down here, integrate that coefficient of the y. Then put that in the power of an exponential, and that creates what's called the integrating factor for this differential equation. Now, what we use that integrating factor for is to rewrite this differential equation into a more usable form. We do that by multiplying the differential equation by mu of x. Okay? So take this e to the integral of p of x dx and multiply the entire differential equation by it. And we get this. Okay? Now, the reason this is useful to us is what we have on the left-hand side is nothing more than the derivative of the integrating factor times y. In other words, if we take our integrating factor and we multiply it by y, and then consider what would the derivative of this product be. Well, the derivative of this product, according to the product rule, is going to be the derivative of this first term, which is the derivative of the power, which is going to be the derivative of the integral of p of x, which is p of x, times this function. So it's going to be p of x times e to the integral of p of x dx, which is times y, which occurs here. Then it's going to be this function times the derivative of y, which simply occurs here. If you apply the product rule to this form, you get this up here. Now, on the right-hand side, we continue with what we have. But what you notice about that right-hand side, it's all in terms of the variable x. There's no y's there. Okay? So we certainly have not separated the variables like we learned about in the previous section, right? I've got x's and y's both mixed up on the left, but on the right I only have x's. What is significant, though, is that I have the left-hand side written as the derivative with respect to x of this. And that means now if I simply integrate both sides, this integral will cancel with this derivative. These cancel. And so on the left-hand side, you've got the integrating factor times y equals, on the right-hand side, the integral of the integrating factor times the right-hand side that you started with up here. Okay? Once you've solved this integral, you simply divide by this term and you've got y by itself. You've solved for y. There's your solution. Now, this looks a little bit intimidating, I think, because you look at this and you see the integral of an expression with an integral within it, and down here, an integral occurring here as well. What I want to point out to you is that in practice, this really turns out to be much easier, because you're going to be evaluating these integrals as you go along. You're not going to be writing e to the integral of p of x step by step. You're going to just evaluate that integral and get a function to plug in there. Okay? All right. So we are ready now to take a look at solving some example problems. Okay? We're going to take a look at first just a little bit of practice in determining whether the equation that you're given is a linear differential equation or not. Okay? So the question is linear or not. And the first one to consider in the exercises is 208. dy dx equals x squared y plus sine of x. And the question is that a first order linear differential equation, or is it just linear? Okay? They're all going to be first order because we'll just have dy dx's in our examples, but is this a linear differential equation or not? Well, you can certainly rewrite this, y prime minus x squared y equals sine of x, and that it fits the definition of the first order linear differential equation in standard form. The derivative of y minus some function of x times y to the 1 power equals some function of x. So in this case, p of x is negative x squared, and the q of x is the sine of x, in matching up to this definition of the first order linear differential equation in standard form that we previously discussed. Okay? All right, so yes, this is linear. 210. We're considering dy dt. That is a typo probably, plus y squared equals x. Now, not only is there a problem here that it's dy dt and you've got x's in the problem, the author probably meant to write a t here or an x here. But disregarding that, this is not going to be a linear differential equation because the dependent variable, y, the one you have in the numerator, is not to the first power. So that's not linear. How about 212? Y prime equals y plus e to the y. This is also not going to be linear because of this right here. Right? You can't have e raised to the y power and have this being a linear differential equation. Okay? All right, so now once we get this basic understanding of what our linear differential equations look like, let's try in problem 224 to actually solve. In 224, we have y prime equals 2y minus x squared. So in standard form, we bring the 2y to the left. Okay, that is the standard form that we talked about here, where the p of x is simply the negative 2 and the q of x is the negative x squared. Okay, so now let's find the integrating factor, the mu of x. Well, that's e to the integral of the coefficient of the y, so e to the integral of negative 2. And so that gives us the integrating factor to be e to the negative 2x. And we can ignore constants of integration when we're finding the integrating factor. They're going to be inconsequential, as it turns out. So just don't bother with them. Okay? Now, if I take this differential equation and I multiply it by the integrating factor, that's what I would get. Everything got multiplied in this differential equation by e to the negative 2x. Okay? This then simply becomes the derivative of the product of the integrating factor and y. And you can do a quick double check. The derivative of e to the negative 2x is negative 2e to the negative 2x times y, so the derivative of this times this would be here. And then e to the 2x times the derivative of y would be here. All right. Now, since this is the derivative with respect to x of this product, I can simply integrate both sides. And that integral is going to cancel that differentiation. On the left, you'll have e to the negative 2xy. On the right, I have to integrate this negative of x squared e to the negative x dx. Now, when we carry out this integration, I think you can imagine how we're going to do that. All right? This is a power of x times an exponential. That is integration by parts. And I'm going to spare you the gory details of going through that integration, and we're just going to write down what you get when you've actually evaluated this. Okay? So we get 1/2 x squared plus 1/2 x plus 1/4 times e to the negative 2x plus a constant of integration, of course. Now, final step, get y by itself. You divide both sides by e to the negative 2x. I've written this on the right-hand side specifically with the e to the negative 2x factored out, so it would be particularly easy to see how to do that. Those simply cancel. And so you get on the left cancellation leaving y. On the right you get what's in the brackets. And then this constant is divided by e to the negative 2x. We'll bring that up. See e to the positive 2x. And there's your solution to 224. Okay? All right, let's take a look at problem number 226 next. In 226, we have x plus 2 times y prime equals 3x plus y. Again, you need to write this in standard form to understand it. So that means I'm going to have to bring that y over to the left. And then I have to get the coefficient on the y prime to be a 1. So I have to divide everything by that x plus 2. Now I'm going to find the integrating factor for this expression by taking the p of x to be negative of 1 over x plus 2. There's the calculation I have to do. Now when you integrate 1 over x plus 2, you just get the natural log of x plus 2. That negative in front can come up as a power, which means you're flipping the x plus 2 to the reciprocal, and then the e and the ln, they cancel each other. So your integrating factor turns out not to have an exponential in it at all after you've done the simplification. It's just 1 over x plus 2. Come back to your differential equation. Multiply the entire differential equation by 1 over x plus 2. Which means, of course, that this is getting multiplied by itself, becoming squared. Same thing on the right. The denominator of x plus 2 is there. You multiply it by another x plus 2. You get this. Now, on the left, this is the derivative of the integrating factor times y. Double check. The derivative of this times y will be this. This times the derivative of y will be this. So the product rule works to show that. Now, if I integrate both sides of this with respect to x, this integral will cancel this differentiation. And I have over here the need to integrate 3x over x plus 2 quantity squared, which works out, again, we'll spare you the details of some of these integrations. To be 6 over x plus 2 plus 3 times the natural log of x plus 2, plus, of course, a constant of integration. Finally, I multiply both sides by the x plus 2 to get the y by itself. That'll cancel this. And I get this. All right, let's try another example. 228. Let's see, that's xy prime equals x plus y. So of course, to put this in standard form, I have to do a couple of things. One is move the y to the left. Second is I have to get rid of this x, so I multiply the entire equation by 1 over x. In other words, divide by x. And so there's my differential equation. I'm going to find the integrating factor based on this coefficient of y. Integrating factor is e to the integral of that coefficient of y. That's, of course, e to the negative natural log of x, which is going to be e to the natural log of 1 over x. And when you cancel, there's your integrating factor, 1 over x. Oops, natural log of x, yeah. So, let's go ahead and multiply by that integrating factor. Sorry, I got a little distracted there for a second. Multiplying this differential equation by 1 over x. I get this, okay? This again should be the derivative of the integrating factor times y. So check. This times the derivative of this gives you that. The derivative of this times this gives you that. If I then integrate both sides with respect to dx, and then multiply, I've got my solution. Okay? All right. How about we take a look at 230? Y prime is y plus e to the x. So of course in standard form, you move the y over. I have to find the integrating factor. E to the integral of negative dx. That's e to the negative x. there's my integrating factor. So the integrating factor, when multiplied through the differential equation, gives me that this is the derivative of the product of the integrating factor times y. And over here, these cancel, giving you a 1, of course. Now, once you get really comfortable with finding the integrating factor, you don't have to actually show the step of multiplying the entire differential equation by the integrating factor and then collapsing this into the product rule. You can jump directly to the integrating factor times y being differentiated. But I would recommend you only do that once you're really comfortable with knowing you're getting the correct integrating factor. Because think of this step as when you multiply through and you check that this collapses into the product rule as a check of your work. Okay? Alright, now if I integrate both sides, e to the negative xy is x plus c. You multiply both sides by e to the x to get rid of that. And there's your solution. Okay. Let's try number 232. In 232, we have y prime plus the natural log of x is y over x. So of course I have to bring this y over x to the left. Let me write it that way. And I have to bring that ln of x over to the right. Okay, I wrote it this way here so that I can clearly see the integrating factor is going to be calculated as e to the integral of negative 1 over x. So that's e to the negative ln of x, e to the ln of 1 over x when I bring the negative up, and those cancel, giving me 1 over x. So now, the idea again, if you multiply the differential equation by 1 over x, the left hand slide collapses into the product rule, simply showing that the product of 1 over x times y will be what appears on the left, and on the right you'll have the 1 over x times the negative ln of x. So there I skipped the step of showing multiplying the entire equation by the integrating factor, and I jumped to what I know should happen. The derivative of the integrating factor times y will be the integrating factor times the right-hand side. Okay, again, only do that if you're really comfortable with knowing you got the integrating factor correct, and that you're comfortable with knowing or remembering that the right-hand side must also multiply the integrating factor. That's easy to forget sometimes. Now if I integrate both sides, this integral cancels the derivative, and so on the right I have to integrate negative ln of x over x. That's negative 1/2 ln squared of x plus a constant, and now I multiply both sides by x to get the y by itself. And there's the solution to that differential equation. Alright, so let's take a look now at some initial value problems, which of course are done basically the same way, except that we have to then solve for the constant of integration. So we'll start with problem 242. In 242, the author asks us to solve this initial value problem by using integrating factor, and the differential equation part of this is y prime equals y plus 2x squared. The initial condition part of it is that y, when evaluated at x equals 0, gives you a y value back to be 0. Okay? Alright, so take this differential equation, write it in standard form. The integrating factor is going to be found by using this negative 1 as the coefficient of y. There's your integrating factor, e to the negative x. I multiply the entire equation by e to the negative x now. And that left-hand side will then collapse into the product rule applied to the integrating factor times y every single time. On the right, 2x squared e to the negative x. And now in this setup, I can integrate the left to cancel the derivative, and integrate the right because it's only a function of x on the right. E to the negative xy, and so now I have to integrate 2x squared e to the negative x. When I do that, I get negative 2 e to the negative x times x squared plus 2x plus 2, all plus a constant of integration. And again, the process you use there, integration by parts, will do that for you. Okay? Now I need to divide both sides by e to the negative x. That's going to cancel that. That's why I wrote it this way with that e to the negative x factored out, so you can see the cancellation easily. And when you divide c by e to the negative x, you can just write that as c e to the x. Okay? All right, now we can apply the initial condition. Applying the initial condition will solve for the value of c. Again, the initial condition says if you put in 0 for x, the y value you'll get will be 0 as well. So put in zeros for the x's and the y's. Zero is negative 2 times, all that's left in here is a 2, c e to the 0 is c. If negative 4 plus c is 0, then c is 4. And so the particular solution to this is the negative 2 times x squared plus 2x plus 2 plus 4 e to the x. And there we have it. Okay. Let's take a look at number 244 next. X squared y prime equals xy minus the natural log of x. And the initial condition that you're provided is that when x is 1, y will be 1. All right. So we need to write this in standard form. X squared y prime minus xy equals negative ln of x. And then I need to get rid of this x squared. So I divide by x squared minus 1 over xy. And when I divide this, negative ln of x over x squared. Okay? Always, this left-hand side is going to become the product rule applied to the integrating factor. Okay? Let's see what that integrating factor is going to be. E to the integral of negative 1 over x dx. That's e to the negative ln of x. That's e to the ln of 1 over x, which is 1 over x. So my integrating factor is 1 over x. 1 over x times y, therefore, is what I differentiate on the left-hand side to reproduce this multiplied by the integrating factor. And when I multiply my right-hand side, I get negative ln of x over x cubed. All right, now integrate both sides. The left just becomes 1 over x times y. On the right, when we carry out the details of this integration process, we get ln of x over x squared plus 1/4, 2x squared there, 1/4 x to the negative 2 plus c. Okay? Now, you know I'm going to multiply by an x to get y by itself, of course. Once I see that c appear in the problem, I can decide to solve for it. I don't have to carry it on and solve for it later. Okay? So I can go ahead and apply that when x is 1, y is 1. 1 over 1 times 1. Ln of 1 over 2 times 1 squared plus 1/4 times 1 to the negative 2 plus c. The natural log of 1 is 0. That goes away. 1 times 1 This is 1/4 times 1. You get that c has to be 3/4. And once you know that c, you can go ahead and write your solution, right? 1 over x, y, is ln of x over 2x squared plus 1/4 x to the negative 2 plus 3/4. And when you multiply by x, that means y is ln of x over 2x plus 1 over 4x, you cancel one of the x's, plus 3/4 x. And there's your solution to 244. All right, let's try number 246 next. In 246, lined up a little better. There we go. We have x, y prime plus y. I'm sorry, x, y prime equals y plus 2x ln of x. And the initial condition is that y, when evaluated at x equals 1, is going to give you back 5. Okay? All right, so let's write this in standard form. I need to get rid of the x, dividing everything by x, and I need to move this y over. So doing both of those simultaneously, dividing by x, canceling these x's and putting an x under this, and moving that y over, I get y prime minus 1 over xy equals 2 ln of x. Okay? So calculating my integrating factor. This is the same integrating factor we just did, right? In the previous two back, I believe, right? So when we calculate this integrating factor, it's just going to be 1 over x. Okay. That was the previous problem, 244, same exact integrating factor. Okay. You multiply by 1 over x. The left-hand side becomes the product rule. On the right-hand side, we get this. Okay. All right, now if I integrate both sides, I get 1 over xy equals the integral of 2 ln of x over n, which is just, since the derivative of ln of x is 1 over x, you're getting ln squared of x plus a constant. Now go ahead and solve for that constant right now if you want. X is 1 and y is 5. 1 over 1 times 5. Ln squared of 1 plus c. The ln of 1 is 0. 5 is c. Which means when you plug in c to be 5 and you multiply by x, that you're getting your solution to be y is multiply by x, x ln squared of x plus 5x. And there you have it. All right, I'm going to skip to 250 because I believe 248 the author made an error in writing the problem and just hasn't realized it yet. In 250, y prime is 2y plus xe to the x. And the initial condition, when x is 0, y is 1. Okay, so standard form's pretty easy here. Just bring this 2y over by subtraction. Find the integrating factor. E to the negative 2x. That's what we're going to multiply everything by. So the left-hand side becomes e to the negative 2x times y differentiated. And the right-hand side is going to be xe to the x times e to the negative 2x. Which becomes xt to the negative x. Now I can integrate both sides. And when you integrate xe to the negative x, you're going to use integration by parts again. and that'll work out to be negative x e to the negative x minus e to the negative x plus a constant. Go ahead and find the constant. When x is 0, y is 1. X is 0, e to the 0 is 1 times y is 1 is 1. 0 times 1 is 0. Negative 1 plus c, c is 2. So when you solve this for y, multiplying both sides by e to the 2x, you get negative x e to the positive x minus e to the positive x plus c e to the positive 2x, where c is 2. We just already discovered that. Okay? And there you have it. All right, so that's enough of solving some of these basic problems from 4.5. Now, what I'm going to do is stop this video here, and I'm going to actually start a new video for section 4.5 where I talk about one specific type of problem to consider and several ways to view that problem. Okay, so it's going to be like a detailed analysis of one conceptual problem to consider. All right, again, for now though, for you to be able to work section 4.5, this video that you've just watched is sufficient. You should be able to work the types of problems you need to be able to work as appropriate for your level, okay? So let's go ahead and stop this, and I encourage you again to ask questions, communicate with me if you have problems, and I look forward to communicating with you if I can help you in any way.